では次にジョージ・ワシントン大学のドクター・ネーゲルからネーゲルさんからローエナジー・ニュークリア・リアクションズ・ロバスト・リザルト・クローシング・ポテンシャル・クリティカル・チャレンジというテーマでご講演をしていただきたいと思います。
So thank you very much for the introduction and Son for the opportunity to participate in this meeting. I have my friends in the front row conditioned to tell me to slow down if I talk too fast. That's a problem. So we'll see how this goes. Now I will start at a personal note. I've been working for 55 years. Interesting projects, important projects. So the question comes up, why am I not retired? And the answer is very, very simple. I'm having too much fun working on low energy nuclear reactions. They're very important results, incredible potential, commercial potential, okay, which is one of the reasons we're all here. And yet there are very, very difficult challenges. So I would like to share with you both information and some of my excitement on working in this field. Okay, now there are problems with the field, as most of you know, and one of them is terminology. We don't really understand what's going on, so we really don't know what to name the field. And this is a collection of all the names I could find. The ones above the line are personal names, and these are company names that have been given by these indicated companies. Of course, I'm not going to go through this. But the point is that when you get into this field, when you look at this field, there's a very, very important challenge on the terminology, and it's complicated because on top of everything, there's a software company called Cold Fusion. So when you do searches, you turn up things that you don't even want. Okay, the other thing that's important to realize before I get into the bulk of the talk is that the field has two branches. Originally, it was electrochemical loading of deuterons into palladium, as you know, started by Fleischmann and Pons, but practically not that important because it's limited by the temperature of the boiling of water or molten salts or whatever. Okay, it's of scientific interest, at least for the near term. Now, early in the field, Piantelli, an Italian in the 90s, started gas loading of protons into nickel, and you've heard some of that today, of course. It has the nice feature that it can reach high temperatures, temperatures above 1,000 degrees. Temperature's good for making electricity, okay? So that almost certainly is the basis of the first commercial LENR products. Okay, so here's an outline of the presentation. As important as the transmutation work is, it's first and foremost about making energy. Okay, so I'm going to try to set LENR in the current energy context using a couple of graphics. And then I'll give you the bulk of the talk on an overview of LENR. And the way to view this is that you've heard a lot of details now. I'm going to back off, 30,000 foot viewpoint, if you will. Take a look at the field as a whole and offer you a framework that I hope you can remember in considering the field. Then I'll talk some about energy gains, and if I run into you on the street someplace and I ask you what's the most important thing I had to say, it's energy gains. Okay, so I'm not going to spend a lot of time on it, but it really, really is critical. Talk about some product development, a new industrial association that we formed, and then I'll have a wrap up at the end. I'll summarize the most important points. So let's start with the energy context by looking at the flow of energy in the United States. This is for the year you see 2013, measured in quads, quadrillion British thermal units. Okay, this is where the energy comes from. The big ones, the black bars, indicate the fossil fuels, about 75%. The size of the boxes, the sizes are not to scale. So they say this, coal, petroleum, and natural gas are about 3/4, and the rest is 1/4. So electricity generation is done as indicated from these sources. The energy, electricity and otherwise, flows to residential, commercial, industrial, and transportation uses. And then it goes away on this side. And the important thing here is that the actual use of energy is 38 watts, and the energy that's not used is 59. So there's tremendous gains for energy conservation, but they're not going to solve the problem of the growing global population on one hand and the increase in per capita energy on top of that, okay? So one of the reasons for showing this is that you see things that are old and big, hydro, and not as old, solar and so forth. they're thin lines compared to what's here now. So, you know, there are people who think that LENR is going to solve the energy problems for the world. And it could, but it's first got to get on this scale. Okay, it's got to be productized, be acceptable commercially, and then grow in size to it starts to rival some of these existing energy sources. So there's a ways to go. Okay, and it isn't going to happen fast, but there's a high probability that it will happen. Now closer to home, here's the energy flow for Japan in the year 2011. You see it's out of date, but it really tells essentially the same picture. Coal, oil, and natural gas are the big things. But this shows the dependence on imports. So one of the reasons I'm so enthusiastic about what Clean Planet is doing, one of the reasons I